In integral calculus, elliptic integrals originally arose in connection with the problem of giving the arc length of an ellipse. They were first studied by Giulio Fagnano and Leonhard Euler. Modern mathematics defines an elliptic integral as any function f which can be expressed in the form where r is a rational function of its two arguments, p is a polynomial of degree 3 or 4 with no repeated roots, and c is a constant. In general, integrals in this form cannot be expressed in terms of elementary functions. Exceptions to this general rule are when p has repeated roots, or when r, x, y, contains no odd powers of y. However, with the appropriate reduction formula, every elliptic integral can be brought into a form that involves integrals over rational functions and the three Legendre canonical forms. Besides the Legendre form given below, the elliptic integrals may also be expressed in Carlson's symmetric form. Additional insight into the theory of the elliptic integral may be gained through the study of the Schwarzer-Christoffel mapping. Historically, elliptic functions were discovered as inverse functions of elliptic integrals. Argument notation: incomplete elliptic integrals are functions of two arguments. Complete elliptic integrals are functions of a single argument. These arguments are expressed in a variety of different but equivalent ways. Most texts adhere to a canonical naming scheme, using the following naming conventions. For expressing one argument, I plus or minus, the modular angle. K equals sin I plus or minus, the elliptic modulus or eccentricity. M equals K2 equals sin 2I plus or minus, the parameter. Each of the above three quantities is completely determined by any of the others. Thus, they can be used interchangeably. The other argument can likewise be expressed as I, the amplitude, or as x or u, where x equals sin I equals Snu and Sn is one of the Jacobian elliptic functions. Specifying the value of any one of these quantities determines the others. Note that u also depends on m. Some additional relationships involving u include: the latter is sometimes called the delta amplitude and written as I equals dnu. Sometimes the literature also refers to the complementary parameter, the complementary modulus, or the complementary modular angle. These are further defined in the article on quarter periods. Incomplete elliptic integral of the first kind: the incomplete elliptic integral of the first kind f is defined as. This is the trigonometric form of the integral. Substituting, one obtains Jacobi's form. Equivalently, in terms of the amplitude and modular angle one has. In this notation, the use of a vertical bar as delimiter indicates that the argument following it is the parameter, while the backslash indicates that it is the modular angle. The use of a semicolon implies that the argument preceding it is the sign of the amplitude. This potentially confusing use of different argument delimiters is traditional in elliptic integrals, and much of the notation is compatible with that used in the reference book by Abramowitz and Stegum and that used in the integral tables by Gradzhian and Rezheik. With one has. Thus, the Jacobian elliptic functions are inverses to the elliptic integrals. Equals notational variance equals. There are still other conventions for the notation of elliptic integrals employed in the literature. The notation with interchanged arguments, f, k, I, is often encountered. And similarly, k, I, for the integral of the second kind. Abramowitz and Stegum substitute the integral of the first kind, f, I, k, for the argument I in their definition of the integrals of the second and third kinds, unless this argument is followed by a backslash, that is e, f, I, k, k2, for e, I k2. Moreover, their complete integrals employ the parameter k2 as argument in place of the modulus k, that is k, k2, rather than k, k. And the integral of the third kind defined by Gradzhian and Rezheik, I, n, k, puts the amplitude I first and not the characteristic n. Thus one must be careful with the notation when using these functions, because various reputable references and software packages use different conventions in the definitions of the elliptic functions. For example, some references, and Wolfram's Mathematica software and Wolfram Alpha, define the complete elliptic integral of the first kind in terms of the parameter m, instead of the elliptic modulus k. Incomplete elliptic integral of the second kind. The incomplete elliptic integral of the second kind E in trigonometric form is. Substituting, one obtains Jacobi's form. Equivalently, in terms of the amplitude and modular angle. Relations with the Jacobi elliptic functions include: the meridian arc length from the equator to latitude is written in terms of E, where A is the semi-major axis, and E is the eccentricity. Incomplete elliptic integral of the third kind. The incomplete elliptic integral of the third kind I is, or the number n is called the characteristic and can take on any value, independently of the other arguments. Note though that the value is infinite, for any m. A relation with the Jacobian elliptic functions is: the meridian arc length from the equator to latitude is also related to a special case of I. Complete elliptic integral of the first kind. Elliptic integrals are said to be complete when the amplitude I equals I/2 and therefore x equals 1. The complete elliptic integral of the first kind k may thus be defined as, or more compactly in terms of the incomplete integral of the first kind as. It can be expressed as a power series, where Pn is the Legendre polynomial, which is equivalent to, where n denotes the semifactorial. In terms of the Gauss hypergeometric function, the complete elliptic integral of the first kind can be expressed as. The complete elliptic integral of the first kind is sometimes called the quarter period. It can most efficiently be computed in terms of the arithmetic geometric mean. Equals special values equals relation to Jacobi I function equals, the relation to Jacobi's I function is given by, where the norm Q is, equals asymptotic expressions equals. This approximation has a relative precision better than 3a, 10^4 for k.